let's start then today's class. So let's see what we have done so far. So in the previous class we have proved that if f is weakly, f have weakly iterates in the interval of 0 to 1, then it will automatically uh, imply that f at every point of this domain of f, that means every point, whatever point I will take from the interval 0 to 1, at every point f has sensitive dependence. And what does the sensitive dependence? We have defined that. What does mean the sensitive dependence? Let me read this statement. So for all there exists a delta constant which is called the sensitivity constant, and for all x which for all interval which contain a point x, there exists a y which is also exist in this I, and there exists n, and for which these 2 points from the same interval I, their initial distance was very small. If we choose such interval, and you will find that after n iteration the distance between these 2 points x and y, that means fn x and fn y, is at least delta apart from each other. So this is called the sensitive dependence of the initial conditions, and we have proved that any weakly iterate map has this dependence. And how we have proved that? Yeah. Hi Subhusari. Good morning. How was your interviews, PhD interviews? Oh, okay, okay. So so we have proved that the sensitive dependence. Now we have seen an example that for these function fx equal to half x does not have sensitive dependence, whereas fx equal to x square contain the sensitive dependence at x equal to 1. And we've also seen why this is happening, because these function f x equal to x square, after nth iterate it becomes steeper, and if we increase in, the steepness become increasing and increasing. That's why the after nth iteration a1 will be go to the point 1, but any nearby point will go less than 1. So that's why it's contain the sensitive dependence, and we prove it by the spike lemma. Through the spike lemma, let me go through the proof once. So by using spike lemma, if I suppose a point x, and then I will choose interval I, and since spike lemma says every weakly iterates, means that there exists n for which one hump of fn and base will contain in this interval I. So this is spike lemma, and if we know that in this interval which contains the point x there is a hump, then we know that since this hump goes from 0 to 1 continuously and 1 to 0 continuously, then we know that the point at which this fn assume the value 1, this also contain in this interval I. So that's why we prove that whereas these 2 points remain initially very close, but after nth iteration it becomes at least half apart from each other. So that's how we prove these sensitivity. Now today we're gonna prove the dense orbits and the transitivity. What does this dense orbit means? So here you see, whenever we are saying the chaos, we to check whether or not the system is chaotic or not, we have to take 2 points. One is x, orbit of x, another point is orbit of x prime. If we say these 2 points are close remain initial, and after iteration it will become far apart from each other. But is it true that the chaos manifests itself whenever we are taking or taking two initially close point. No, it's not. The chaos itself present in a single orbit. So what does this means? So whenever, if you recall that when we have plotted these orbit diagram or bifurcation diagram, then you seen one thing, that after some periodic appearance, there are dense points appearing there. So as if that iteration of these points are spread it over all over through this interval 0 to 1, and it spread it very densely. So then we have concluded that maybe this region contain chaotic. This region is chaotic region. Why it is chaotic? Because the orbits become very dense. It does not go towards any kind of attractor, any periodic points, but it roam around this interval 0 to 1. uh, it wanders every point, every interval of this 0 to 1. So that's why we call this is chaotic. So chaotic does also means the dense orbit. So let's see a computer example. It will be yeah, let me do one thing. Yeah, you see that this point, this is in the 16. You will see that the points, these dots are the iterates or nth iterates of this point 2. So you see, whenever I here I only take only a 14 iterate. Now if I increase the number of iterates, you will see these become denser and denser. So let me show you this. So I have taken here 15 iterates. If I say 100 iterates, let's see. You see these become quite dense, and whenever I will increase the iterates, it will become dense and dense. And from the single orbit, you can see that it is not at all a regular orbit. This is a chaotic orbit, because you see there is no periodicity, no attractor, and this is not converging toward a fixed point. So and this means this it will roam around in the interval 0 to 1 and very densely. So that's why the dense means dense orbit also a property of the chaos. So let us define what this dense orbit means. So to let me 15. So yeah, so dense means, so let us define dense. First here see what the dense means. Dense means if you choose any point. Suppose here I am choosing the point 2. Now if you choose any point and you choose any interval. Interval means this shaded gray region. This interval means I am taken here interval from point 7 to point 9. So point 7 to point 9 is the interval. So dense, the mathematical definition of dense means if I choose any point x and any this type of region, it doesn't matter how big or how small and where it is, any interval, you will find that the one ends here, n is 4. There will you find that one n for which the x to the power n, that means xn, contains in the interval, this interval. So that means x4 is in the my this random interval. So that means wherever you choose your interval, you will find one point, one iterate of this point 2 inside that interval. So that says that this point 2 after iterates, it will visit every possible interval between 0 to 1. So this means the dense. That's why you will see that why this y direction, these dots become denser and denser when I increases the iteration. The initial condition actually wander around every possible interval in the code open. So that's it. Now this is the definition. So let me go back here. Definition is, so suppose dense orbit of x0, this means for all interval I or j, for all interval j which contains this point x0, which contains this point x0, there exist, okay, there exist a n which obviously belongs to the natural number, such that if n x also belongs to this j, here the symbol is should be this means we will find a interval, so not this. So this is wrong, I think. So it does not require this, the interval should contain this point x0. So for every interval j, you will find an n that such that f and x, that after nth iterate the point will be there, nth point will be there, nth iterate point will be there in j. So but one thing is very difficult here. To prove this statement in general is very difficult because it needs topology. But in these lectures we did not we actually we I assume that we don't know the topology. That's why what mathematicians do, so they, instead of this denseness, they prove the transitivity, and it does actually mean same. Let me, transitivity means not here, you see that here I choose a single point, but instead of single point I will choose a interval, suppose I. So I will choose some interval and I will say that if I iterate all the points from this interval, so if I iterate all these points at some n, this interval and this interval, choosing interval, will intersect with each other. So let's see again on one example from here actually. So here let me draw 0 0 5. So you see here, so I am plotting that tinier interval between here between 2 to 0.22 0.00 0.00 0.2 to 0.2005. So this is a very tiny interval. So I am iterating this interval. So when I iterate this interval, so it, since these two points are very close, they remain very close, and you will see this is the first iterate, this is 0th, this is first, this is second iterate, this is third iterate, and you see at the fourth iterate this interval and my randomly choosing interval j intersect with each other. So here the value that exists, the value of n for which this interval j interval intersect with each other, that value of iterate is n equal to 4. So in general, what is the definition? So let me define definition of the transitivity. Okay, is it clear, Subhadaji, that the what does this transitivity means? Okay, so let's see what is the definition of this transitivity. So a mapping f 0 to 1, which is a compact map. That means it maps this interval onto this interval, same interval. That means domain and codomains are same, is transitive if for every pair for every pair of subinterval interval I and j, subintervals I and j, there is an n such that such that if in I intersection of j will be not phi. So that means it does means that the intersection exists, that if n and j intersect at some point. And in our previous example we have seen that this intersection happens at 4. So let me give another example. Suppose that mm, instead of these, let me point 1 0 point 1 and 0 point 0.1 0 0 5 maybe. Let us do this. Let us see again where does this. Okay, it also intersect here the intersection of this point. So let me take another big interval. Maybe let me do its 0.2, maybe 0.1 maybe. Yeah. So so you see here also you see that this is quite a large interval, 0.1 interval. So whenever I am iterate this 0.1 interval, you will see that at the first iteration there is no intersection, at the second iteration there is no intersection, third iteration is same, but at the fourth iteration you see my interval is this. So here so you see that at the interval, so at the fourth iteration the interval remain the interval or this smaller interval intersect with this interval j. So that's it, this means transitivity. So that means every interval of this I, whatever interval I choose, it will at some point will intersect with, is in the in the mathematical language we say this, for every I, for all I and for all j there exists a n which obviously belongs to natural number, such that if n I intersects j is phi. So that's it. Now the proof is very simple. We again use the spike lemma. So here the lemma is, so what do we want to prove? So let me write the lemma. So if 0 1, so this is a compact map, has wiggly iterates, then f is transitive. So what does this wiggly means? Let me recall. Wiggly iterate means it will be a one hump map. F is one hump map between 0 to 1, and it will remain between, this is also 1, it will remain between 0 to 1, and up to this point is continuous, and then for continuously strictly increasing to 1, and then it is strictly decreasing to 1. This is called one hump map. One hump map. Now if this one hump map has two properties, one is nth, that is nth iterate of this fn contains, this is one hump, contains 2 to the power n minus 1 hump, and second, this the base, the base of this is the base of the f. So base of the highest, base of the maximum hump will decrease as n goes to, n tends to infinity. The hump, base of the hump will goes to 0. So if these two property holds by any function, this is called the weakly iterates. So it says that if f is weakly iterate, then f is transitive. So, and we have already seen from previous lecture that weakly, if f is weakly iterate, that means it contains the spike lemma. It should spike lemma, that means whatever small interval we choose will get a hump like spike in the smaller interval. So that's why it's called the spike lemma. So I will see the spike like structure. So I will find the n, and for every interval I will get a one hump whose base is contained in the side. So this is called a spike lemma. So let us use this spike lemma since it is weakly iterate. So what I want to, so I have to choose one interval j and I. Suppose I choosing the interval j here. So this is my j, suppose this is my interval j, and suppose this is my interval I. Now I have to prove that if I iterate the points from this interval, at some point it will intersect this. So what I will do, I will just simply apply the spike lemma. Since it's a weakly iterate, so it, that means I will get a one hump, I will get a n whose base, we will get a one hump whose base will contain in this hump. So this is, I will get a n, so this is fn. So the base of this one hump will contain in the interval I. Now you see, so since this interval is continuous, so suppose this is a point from I, so every point from I will goes from, so here it is 0, here is something, then at this point is continuously increasing continuously from 0 to 1, assumes f to the power n, assumes every possible values between 0 to 1. Here something value is suppose 0.5, here point not 0.5, 0.2, then point 2001. It will continuously assumes the value 0.1, and then from 1 it will continuously decrease to 0. So that means it will contains, so it actually intersect here. So here this j, how much point it contains. So from here to here, these points of fn I. So suppose these actually are iterates of tiny interval of this, suppose tiny interval of this, and here also again these points also belongs to j, and it's also a part of fni. So that means fni intersect j, I will get these many points. So these and these many points. So this is not equal to 5. So that means I can choose any interval I for which these transitivity satisfied. That means for any I, if I iterate this I will get a n which will intersect the any interval j. So that means if I choose a interval, very tiny interval, it will wanders around every possible interval of the codomain. This axis is called the codomain. Now anyone can say that if weakly iterate was not there, then maybe it is true. So suppose that is, let me that it is not true, let me show you. Suppose this is a one hump map. suppose these kinds of one hump map. This is one hump map, and suppose this is J. Now one can say that here also whatever this is not required any n, and spike lemma here also it actually intersect this and this point. So you can say this is transitivity, but no, that is actually not true. Suppose I am assuming here a interval, suppose here a interval small I. So now if you see that the if that the point after iteration, the point will be here, iteration after the iterated point of this interval will map to this region. So this region, and you see these region, these parts, actually these parts are not intersect, this part is not remain in this interval J. So that means this I, this f of I intersect J, since inside the J there is no point of I, so only fi is contains this much points, and which is outside this J, that means it is equal to phi. So that means if spike lemma was not there, that means we cannot prove this transitivity. So Bodaji, is it clear, the proof of the transitivity? Okay, if it is clear, then let us move to the proof of the dense periodic points. Let me show dense periodic point. Dense periodic points. So what does means the dense periodic points? First let us clear that. So dense means, so if I choose any interval between 0 to 1, I will get at least one periodic point inside this interval. So that's why it is called the dense. Previously also the the meaning of dense is same. So if I go here, oh, it is not there the dense, so I mathematically plot it. So I plot it and show you. So let me go there. So here also, if you recall the what is the meaning of the dense, so let me point 1. So I have said that the meaning of the dense means, so for every interval this I will find one iterate of this any initial condition will be in this between this in the interval, in this interval. So that's why it is dense. That's what it means, that after iterates it will go, it will wonders every possible uh, domain, every possible interval of that, if it's in its codomain regime. So that's why it is dense. Now here also the dense periodic means what I want to prove. Dense periodic means I will prove that whatever interval you choose, you will find one periodic point there. So let us first write the lemma, then I will prove it. So I want to prove it for weakly iterate. Why I want to prove it for weakly iterate? Because we know that the logistic map actually a weakly iterate. That's we have proved that after n iterate, the spike becomes, the hump becomes 2 to the power n minus 1, and the base of the hump decreases as I increase these iterates. So what I want to prove, lemma. So if F is a map which maps 0 to 1 interval onto interval 0 to 1, has wiggly iterates then the set of all periodic points of f is dense in the interval. And we have already defined what is the meaning of dense. So we want to what proof? Proof is that if I give any interval, suppose this is, and here also I will use the spike lemma. So if I suppose this is 1, okay. Suppose this is my interval, I interval. Now I have to prove that for every interval there exists at least one periodic point. So from the spike lemma, what we know, that I will get a one hump whose base will contain in this interval, that I know. Now let us draw the identical line. This is the identical line. This means y equal to x, and this is the fn x. Now what we have learned, that where this line and this curve intersect each other, so that means this point and this point. What does this point mean? This point means this is fn y, this is fn x, actually fn x, and this is also fn x1, this is also fn x2. And we know from this red line, since these 2 points also the part of the red line, so this is y, this means actually x, and here x is, this is x1 and this is x2. So that means since this red line, a part of these points part of a red line, that means we know that fn x1 is equal to fn x1 and fn x2 is equal to x2. And what does it mean? So after nth iteration I will get back the x1 again, so that means it's the nth period orbit. So it's the nth period orbit point. And what does this means? This after nth iteration of x2 I will again get back x2. So I will, in between I will get many other points, but after nth iteration I will get back x2. So that means it's also periodic point whose period is n. This is a periodic point of period n. This is also same a periodic point of period n. So now we know that in this interval there are two periodic points, one is x1 and one is x2. So this is that means it actually satisfies our the definition of the dense. So whatever interval I choose, I will get at least two. Here you see that at least two periodic points. So that means the periodic orbits, periodic points in this interval is very dense. So since the map is wiggly, that means it satisfied the spike lemma. That's why we can say, we can prove that the periodic points are dense in this interval. So now this proof also done. So is it clear, Subhusaji, that why the periodic points are dense in this for the wiggly iterates? Okay. Okay, let me uh, go through that. Now let me again recall from where we have started, and from the next class we will see the fractals. So let us go back to these basics. So what is chaos? So here, so what we have proved, that wiggly iterates have these properties. So A sensitive dependence, then B, transitivity, transitivity, that actually means, and a dense orbit, and E means a dense set of periodic point. This is the three things that this weekly heads. First of all, the first two is make sense, that it means irregularity, chaotic things, that sensitive dependence and transitivity. But what does these things that C, a dense set of periodic points? And we know that periodic point means quite regular motion. So periodic orbit means quite regular in nature. But why this is actually required, or this is there, although we are saying that it is a chaotic orbit? So you see here, if I go here, then here, okay. So here you see that although that there is orbit, but if you draw a tangent to this line, you will find that the derivative, first derivative of this ddx of fn x at x1 or at x2, you will find that the tangent at these 2 points are very larger than 1. So, and we know that since it is larger than 1, although these are the periodic points, these are not the stable ones. So these are the periodic points, but these are not the stable ones. So that means any point, if I start any point neighbor to these 2 points, it will not go toward these points, it will move away from this point. So that's why for existence of the dense periodic point is fine, but these all periodic points are unstable. So that's why whenever initial condition goes very close to a periodic point, it will repeal that the any initial condition. And since there are very dense set of periodic points, so any whenever initial conditions after any iteration reaches toward any particular periodic points, it will repel by that, and it will again go towards some other periodic points, and it will also repelled by that thing, and that's why it's wander around the whole space. That's it. Now that's why in the first sense is looking that it is a periodic point means regular, but it is actually not regular, since it is not stable at all. Now let's go through that. This is the three things that weakly iterates have. Now let's go to this definition of the chaos. Definition of chaos. So this is the definition of the Devaney. He gives it at 1989, and this is Devaney at 1989. So what is this definition? Let me write it. Let B be any interval, P be any interval, we say that F is a compact map, that is it maps this V interval onto this, again the V interval is chaotic, if simply if F has sensitivity everywhere, B same thing, that F is transitive, and C it is periodic points are dense in V. And you see that all the three things are there in the Wiggle iterate. That means we can say that the any Wiggle iterates, a map which have Wiggle iterates, it will be chaotic. So this is a theorem. So it's a simple theorem that I am saying. It is in the written in the mathematical terms. If F is a compact map, 0 to 1 interval map into 0 to 1 interval, and has wiggly iterates, then F is chaotic. Now we have proved that since a logistic map is wiggly in nature at mu equal to 4, then we can now we have mathematically proved that since it is wiggly iterate, and theorem says that since it is wiggly iterate, it actually holds these three definition of the chaos. That's why we can now actually mathematically says that the wiggly iterate is chaotic. That means at mu equal to 4, the logistic map has the chaos in itself. So that's all. Now in the next class I will uh, we will see the fractals, and this is the end of the chaos. Now let me uh, stretch a little more and say these two things. One, that this is the definition of this chaos is not limited to any interval. So it is that if V is any set, not any interval, any set, we can find that in the chaos in the V. So for any set, but for in the any set we have to, in this set we have we have to find a function D, which is called the distance function. Means if I can define the distance in this set D, so this is called the D is a function. D is a function and it is called distance if it holds these three property, that D any 2 points, if I take any 2 points into two elements from this set, suppose x and y. So you see, first of all, the distance between the x, y greater than 0, and x, y that belongs to B. Now d x, y will be 0 if and only if x equal to y. And the second thing is that dxy, distance between x, y is equal to dyx. And third is the distance between the x and z. Suppose distance between the x and z is less than equal to, this is suppose in two dimensional space, this is x and this is z, suppose this point is y, so dxy plus dyz. So if I go back through these points dy and dz, it says that the distance between the x and z is always less than the sum total of x and y and z. So this is, if I can find a distance, then this set will be called the metric space. And for any metric space, this is called V comma D is metric space. So this is quite mathematics, so don't worry about it. So I just let you know that for any interval, so previously we are saying that this interval is real line interval from 0 to 1. Now it not necessarily has to 0 to 1, or for any interval, for any set, if we can define if I define a function, and from that if that function satisfies this condition of the distance, then we call the V and D metric space, and we can actually find the chaos in this metric space. One thing is this, and another things I want to say, since this after definition of the definite, everyone tries to find out that whether or not these three conditions are independent of each other. So thus we can conclude A from B and C together, or B from A and C together, or C from A B together, or from A from we can conclude B C from A. So these kinds of things. But since means if you know about the Newton's law, you know that the first equation of motion, second equation of motion, third, not first law and second law of Newton's third law is actually independent of each other. You can't derive the third law from first and second, or you can not derive any other law from any other combination of two. So that's why these laws are independent each other. So here everyone tries to find out that whether or not these ABC are independent of each other, and there is a beautiful proof and mathematical proof. So I will not go through this mathematical proof, but in 1992 five Australian mathematicians, and that is Bank, Brooks, and Carrions, and Davis, and Stacy, obtain a surprising result that says that actually a very interesting result that says that the sensitive dependence, these these sensitive dependence can be derived from these two things, that if a function is transitive and it has dense periodic orbit in the v, then v means the for this compact function in the interval v, then it will automatically satisfy this condition a. So that means the f of f, this the condition a, that the sensitivity, that whenever we deal with chaos we have actually deal with this, and we know is quite familiarized by the butterfly effect. So butterfly effect is nothing but the condition a. So you see, this butterfly effect is actually seems redundant for proving the chaos. Actually b and c are enough for proving the chaos for compact map. Compact map means when if v means map v into the same region v. So that's it. So that's all for this chaos. From the next lecture I will start the fractals, and I will take maybe 2 class or maybe 3 class. Then after that the fractals will be done. So that's it. So if you have any question you can ask me, or otherwise I will end this class here. And so Bosaji, have you any questions regarding this? Have you any question regarding this? Okay, then thank you for joining. So I am ending this meeting right now. So let's meet at Friday at 11 p.m.